I will be talking about the data parallel deep learning. Hopefully in the past 2 weeks you have learned a lot of things about high performance computing, and then in this morning you learned about the deep learning, all kind of neural network and what it can be, what can we do using the neural network for scientific problems. And so this afternoon, this talk will be combining the high performance computing with this machine learning and deep learning technique. So what we are going to do is to push the deep learning to the high performance supercomputers, so to accelerate the training and inference problem. So what I'm going to do, I will start with why do we need to parallel the deep learning into high performance computers, and then I will say about what do we do. What kind of parallelization scheme we use to distribute the deep learning on large scale supercomputer. And then I will talk about the challenges and tips for data parallel training. And then after that, I will talk about the I/O and data management. And typically people don't talk too much about this, but I envision that this will become an important problem as we have more and more data set. And then at the end, I will present several use cases, mostly from my colleagues in Argonne. So, okay, why do we need distributed training in HPC systems? Well, there's a very good article in OpenAI blog. What it does is it estimates the neural network starting from 2012, where people proposed the AlexNet, which is a very simple deep learning neural net. And then as the time evolves, more complicated came out, like ResNet and VGG, a lot of other neural net proposed by Google. And then the most recent, AlphaGo. So the amount of compute from the most simple AlexNet to AlphaGo is 3 million times more. And this follows a kind of exponential growth. So it doubles every 3.5 months. And that means that as we kind of, the whole field of AI evolve, we are dealing with more and more complex neural net. And also on the hardware side, people start to use the more and more computing resource to work on the AI. Before 2012, basically, people just do it on their laptops, and then they start to use single or couple GPUs on the workstation, and then 10 or hundreds GPUs, and then starting from 2016, there are a big push of the deep learning to these high performance supercomputers. And just to give you a sense that. Quantitatively, and also I would like to point out that starting from 2017, 2018, people start to play around with the neural architecture search, that not only just the neural net designed humanly, but we ask the computer to find out the optimal architecture. So that increased the complexity of this problem by several order of magnitude. And so give you a sense that for this ImageNet model, there's one of them called ResNet 50, which includes 50 layers of neural nets. And to train such a neural net, if you use one immediate GPU, which is M40, at least here, it will take you 2 weeks to finish the training. And the amount of compute is 1 axis flops in single position. And if we put this problem in the most powerful supercomputer we have in current day, which is Summit at Oak Ridge National Lab, which have 200 petaflops performance in double precision and several exaflop mixed precision, then we would, in principle, if everything scales well, we should be able to finish the training in the order of 1 second. Of course, there are a lot of other problems that the I/O and even non-linear job these times, but you get a sense that by scaling this problem in a large scale supercomputer, we'll be able to dramatically decrease the time to solution. And so that's the motivation that we need to push the deep learning into the high-performance supercomputers, that we can accelerate trainings from days, weeks, to hours and minutes. And just a brief summary that there are points that why we need pushing this to HPC is that first, as I said, the complexity of the model increased dramatically. And in particular, now we started thinking about using computer to search the optimal neural network. Then the computer can do much kind of complex way. So I envision that the model complexity will grow very much. Then the second thing is that the amount of data we are dealing with is also increasing significantly. Previously, we are dealing with like megabyte, gigabyte data. Now we are dealing with like petabyte data or exabyte data. So just envision that simply that your neural net scans through this data set in a sequential way will take a lot of time. So it's become increasingly impossible to do everything in a sequential way. So that's why we need to deal with this in a parallel way. And then also, the computing resource developed in kind of more and more from the parallel computing. Like in 2021, we're supposed to have a exaflop machine called A21. So we want to push this so that our deep learning can scale well on this high-performance supercomputer. And the last point is that more and more in the scientific domain, people are trying to couple their machine learning or deep learning into their traditional simulation application, for example, computational fluid dynamics, and which inherently are parallel running on the supercomputers. So it's very important to make sure that the deep learning part of this whole application also run in a parallel fashion. So it will not become a bottleneck for this overall simulation. So that's kind of have a sense that we truly need to have distributed training at large scale. So, and then if we think about how to parallel the deep learning, basically there are two schemes. One is the model parallelization. The second one is the data parallelization. It's more like in the MPI community, text parallelization versus the data parallelization. So for the model parallelization, it basically we have a neural net, and we just distribute these different different neurons to different processors, and each processor only deal a part of the network. And there are the communication among them, which is the data flow from one neuron to the other neurons. And you can think that it's conceptually simple, but in practice it's complicated because we have very complicated neural net, and how to divide this neural net into chunks, and so that each worker can deal with this each part in a balanced way. And also there is since different layers have some dependence. For example, worker 4 will depend on the result from worker 3. So there's also a pipelines issue we need to deal with carefully. So in general, this is kind of complicated, but the second scheme called data parallelization is very simple. Basically, we have a data set and we divide it into subsets, and we duplicate the models. And each models or each worker will work only on a subset of the whole data set. And as they train, they also sync up with each other, so to make sure that the models are the same as the training evolve. So this is the data parallelization. And at high level, and to go a little bit into details, is that in the whole deep learning problem, we're essentially dealing with a minimization problem. So we have a total loss, which quantify how good our model is, and it's a summation of the loss associated with each sample, and omega is a weight. So basically, we're changing the weight and so that the loss will be small. And we want to find a minimum loss for this problem. And typically, like people use as stochastic gradient descent, and there are other optimization methods. But the essential idea is to calculate the gradients of the loss, and then to propose the move forward. And people use the stochastic gradients is that each time we just fetch a batch of data, and then calculate the loss and gradient correspond to that batch, and assuming that this is a good representative of the whole gradient, and then use that to propose the next step. So, and then in the data parallelization scheme, basically the computing part, which we calculate the gradient, is distributed. We have a batch of data. Now we divide this batch of data into several small batches and fit into different workers. So each worker will calculate the loss and gradient associated to the sub-mini batch. And then at the end of each step, they aggregate the loss and weight together so that we can have the total gradient associated to the global mini batch. Then we propose the update, and this update will update the models on each workers. So the model are always sync up together, but all the workers are dealing with different data. So this is the kind of essential idea of this data parallelization. And there is a package called Horovod. How many of you knows Horovod package? How many of you are using Horovod? Okay, I saw a couple of hands. So this is essentially the idea behind Horovod. And then just one important thing is that the gradients are averaged at each step, not each epoch. So each step we need to average all the gradients. And then another thing is so as I said in previous slides, we are dividing this mini batch into several small batches. And there are two options of dealing with is that suppose in the one node training, you have a batch size of 256. Now you are using two nodes to do the two workers to do the training. There are options that the first option, you can let each of them do 128. So then each of them will do a smaller set of this 256 batch size. Well, this is a kind of strong scaling case in the parallel computing. Basically, you fix the problem size, and then once you have more and more workers, you divide this problem into smaller units. And the second option is that if you have two workers, I still let like one worker do the 256 batch. And so overall, I'm actually effectively increase the batch size to 512. So this is called large mini batch training. So basically, if I have n workers, I will increase the global batch size by n times. And we choose the second one mainly because that suppose if we in the strong scaling case, if I have more and more workers, then the work is kind of smaller and smaller. Then I tested this performance that the smaller batch size is not good for the performance for this. This is the ImageNet benchmark, basically saying that if I reduce the batch size, then the number of image I process each node is kind of degrading. So it would be good to keep the batch size per node the same, and globally we scale the whole batch size. And also in this deep learning, we have to scale this learning rate. So suppose you increase the number of workers n times, we have to increase the learning rate by n times also. And the reason is very simple. Because in this optimization problem, at each step we propose a move, right? And suppose we use use smaller batches, we do 2 steps, and now we are using two times of batch, like not 256 but 512, then we still want to reach in the same goal. Then we have to use a larger time step. The learning rate is kind of the time step we use. So if we use the 2 times of the learning rate, then we are able to reach the same goal. And if you're interested, you can look into the mathematical details, and you will understand that why we need to scale the learning rate by twice. And so this is the ingredients that basically in the training we scale the overall batch size and then also scale the learning rate. And people have been studied that actually if we increase the batch size, they find out the optimal learning rate for this optimization problem indeed follow this learning curve. So increase the learning rate in a linear way does kind of give us a better solution. And however, there are some challenges with large batch size training. In particular, that in the beginning, because this is the optimization problem, in the beginning, if we use 2 large time steps, this will kind of, that the optimization hard to find a minimum. So it's not stable in the initial stage to use large time step or large learning rate. So, and another issue is a so-called generalization gap. So if you train your model upon the training set and give a good accuracy on the training, but then if you validate that with another data set in your test set, and you'll find that the test set will degrade it if you use this large batch size training. This is what has been studied in this paper. Basically, across different models, using small batch training and large batch training, for the training accuracy, all are kind of similar. But then if you test the on another, like on your test site, you see that the large batch size typically have smaller kind of score, smaller accuracy. So the reason is that in this minimization problem, there are different type of kind of minimums, and for the large batch size tend to be trapped at this so-called sharp minimum, like very deep minimum. And this sharp minimum is hard to generalize. That, for example, in the black curve correspond to the loss associated with your training set, and the red curve associated with your test site. So for this flat minimum and sharp minimum, they all have like kind of the similar accuracy for this training. But suppose in the training I stay in the sharp minimum, then I want to go to the test site. The same point for the test site will be kind of much higher, the loss. So it's good that if we find the minimum point here in the flat region. So, and people have been studying that large batch size tend to stay in this kind of very, very deep minimum. So it's not good. There are some statistical rule or a reason behind this, which I don't want to go into detail. If you're interested, you can talk to me after the talk. So these are the challenges so people have been proposed to use the warm-up steps. So basically in the initial stage, because it's not stable, so we use the small learning rate and then gradually increase to large learning rate. So after this warm-up step, this solve these 2 issues simultaneously. It stabilize the initial stage of training and also avoid this generalization gap. And the result shown here is for the ResNet 50 trainings. Basically, this going from the small batch size to 256 to 8,000 without using the warm-up step. we will see the blue curve performs worse than the small batch size case. But if we use these warm-up steps, then essentially at the end, it reached the same accuracy. And they study all the way up to 8,000 batch size. So using the warm-up step, they can still reach the same accuracy. But if you further increase, like go beyond 8,000 batch size, then even the warm-up step doesn't help anymore. So we need to kind of think about other ways to make sure that large batch size can still reach the same accuracy as the small batch size training. And people also has an estimation of, like, for different neural net and different data sets, what is the maximum batch size that you can use so that it won't degrade your training accuracy. And just a simple comment is that the maximum batch size is basically set a limit for the data parallelization, because the number of workers should be smaller than the batch size, right? So if each time we process 256 image, then the most is that we can use the 256 workers to process. We cannot go beyond that. So this is kind of set a limit for this scaling, for the storm scaling. So these are all the theory behind this data parallel training. Okay, question?
Do you have similar rules of thumb for model parallelism?
Model parallelization, I don't have it in my slides, but yeah, you can find other things. Yeah, I don't have it here. Yeah, so in this, I mostly focus on the data parallelization, but we can talk after the, yeah. So, yeah, so, and then in practice, there is a package called Horovod to help to distribute your training. And it is very simple. If you have a series code, like you run on your desktop, and to change, you can have a very minimal change to make it run at large scale. And these are the steps that you need to think about or you need to do to change your code to make it run in parallel. The first is to import the Horovod modular. I will show in detail in next slides, but here I just point out there's a couple things you need to do. And then initialize Horovod. This initialize is just like an MPI init in your MPI code to initialize the MPI environments. And the second thing is to wrap your optimizer. So I will say more later. And then scale the learning rate in proportional to the number of workers you use. And the third thing is to broadcast the weights from the worker 0 to all the workers. As I said before, that all the models are duplicated in the workers. So we want to make sure that all the workers have the same model. So right in the beginning, when we initialize the workers, we need to make sure that every workers have the same model. And also in the training, sometimes we cannot finish the training. We will save the checkpoint files, and it's important to just let one of the workers to save the checkpoints, so it won't kind of interfere and write kind of files that it cannot be used later. So just let one worker to do the checkpoint file writing. And the other thing is also regarding the data management, the data, how to read the data sets. As I said, that in the data parallelization, each worker work on different piece of the data set, right? And that's kind of a general assumption. And there are actually two options you can do. The first is that I still let all the workers see the entire data set. And so each worker will read a batch of the data from the data set, but they read randomly. They randomly read all the data. So that kind of so we hope that by this random fashion, they can cover, all the workers can cover the entire data in a faster way. So basically, this is that you don't need to do anything. You just still do it the same way, but then different workers read sample the whole entire data set randomly so that they can cover the whole data set in a faster way. So then you, in that case, you decrease the number of steps per epoch by m times, because you're hoping that in one worker it takes long to cover the entire data set, but now you have n workers. It would be faster to cover the entire data set. This is one of the options, and typically it's the kind of default options when you download the code from Horovod websites, is use this kind of option. The second option is that we manually divide the data set. So we make sure that worker 0 work on this data set and sample data set from this subset, and worker 1 sample this data from the other part of the data set, and so that they won't have any overlap. And personally, I prefer the second one. Yeah, there are reasons, and also it's easier to deal with the I/O part. But as far as I know, both this way works. It won't it will have like very similar accuracy. It won't degrade this performance very much. And these are the examples. If you are familiar, how many of you are familiar with TensorFlow code? Okay, good. So these are the steps I show here. The first one is to import the Horovod modular, and then do Horovod init, like MPI init. And then the second thing is to initially you have an optimizer with learning rate 0.001, but now we use Horovod size is the number of workers. It's just like the MPI size. So we scale the learning rate and then wrap it with the distributed version. So this distributed version of the optimizer will not only just calculate the weight, but also do the aggregation or the MPI or reduce to sum over all the local rates. So they have a global kind of gradients. And then that only rank 0 write the checkpoint file. And the other thing is regarding the data. So here, each rank will see the whole entire data set. And then the number of steps is kind of divided by the number of workers. So it contains fewer steps. And I won't go into detail, and there's examples for PyTorch and Keras. You can find more on this website. And this is just to show that for the ImageNet, I scale it up to on Theta. So I go all the way up to 2,000 nodes, and you can see this white bar is the ideal scaling case, and the blue is the real case. And because of the communication involved, it's kind of degraded from this ideal case, but we still have very good scaling efficiency, which is about 50% or 60% scaling efficiency. And then here shows the total time versus the communication time, the communication overhead. The blue is the total time, and the orange are the communication times. And you can see as we increase, the communication grows. But we also see that, especially from 1 node to 2 nodes, the communications grow by 80 seconds, but the total time only grow by about 20 seconds. That means that there is overhead between the compute and communications. The reason is that we're dealing with deep neural net, and each layer, kind of the communication are independent from the other layers. So they can, while they propagate the neural net, they can do the communications. So they can overlap the compute and communication. And this shows a little bit detail of the MPI profile. You can see the majority of the communication is spent on the MPI or reduce. And lastly, I want to talk a little bit about the I/O part. So we know that we distribute this training, and the compute part is distributed across different workers. So, but in the I/O part, we also need to be very careful that the loading the data also need to be in a parallel fashions. So typically, we need to use some MPI I/O or parallel HDL5 for your own scientific problems. And then also pre-process the raw data. So like if you have image data, you pre-process all the image data like scaling, resize the data, do interpolations, and before the training, so that it will save these I/O times. And then store the data set in a reasonable way. I will say more on the next slides. And also do prefetch. Means that while you do the training, you fetch the data, fetch one batch of data, so that in the next batch the data will already be ready. So this is kind of overlap the I/O time with the training time. And for the data organizations, people naively, for example, for dealing the image, we just save the samples like one image per file. And so this is very inefficient, as this green curve shows, because the files are typically small. And each time when we open the data, open the image, and then read and close, the open and closing create a lot of overhead. So it shows that it's better to save like the one batch of data per file, so that the open and closing won't cause any overhead. And the other extreme is to save the whole data set into one file. But that case perform not good, because the collective I/O performance typically is not good in HPC environments. So overall, like in the intermediate region, save like hundreds of images or thousands of images per file. Not one image per file, not the entire data set per file. And these are some examples. This is, I think, at least present a little bit. This is a cosmology project. We use the deep neural network to classify the galaxy images. There are two types of galaxies, elliptical and spiral. So this is to show the scaling curve, where initially we just use one GPU, and the total training time is 4 to 5 hours. By the end, we use 64 GPUs. The training time only costs about 8 minutes. And this is the overall throughput, like the number of images processed per second. So you can see this increase, and then the overall time to solution decrease. And this is another project, basically use the deep neural network to map the brain image. So the data was from the X-ray, and we use deep neural network to do segmentation to find out all the biological neurons. And then there are two scaling plots shown here. The first one is just show the scaling of the total throughput. If I increase the number of nodes, the number of data, the number of samples I process per second is increasing in an ideal scaling way. But then for the large batch size, because I used large batch size, we use much batch size for large number of nodes, then it might require like more epochs, more number of epochs. So there is a degradation from the ideal scaling for this so-called training efficiency. So train the neural network up to certain accuracy. The last example is the candle benchmark. Here I list this result to show that this is scaling plot, and I/O become a bottleneck. This gray curve is the initial I/O, and then after optimization, the scaling well. But then the I/O still, it looks like the I/O is not scaled well. It's become flat. So there's still room for improvements. Okay, I have about 50 seconds. So the conclusion is that we need data parallel training because the increase of the model complexity and also the amount of data. And the second thing, the data parallelization can scale very efficiently on the HPC supercomputer, as we see from all the scaling plot. And then some tricks that we need to use warm up. We use a smaller learning rate in the initial stage of training to avoid this training instability and also generalization gap. And lastly, we also need to deal with this I/O to make sure that the I/O part will not become a bottleneck to the overall training. Okay, that's all I have. Thank you very much. Any question? Okay.
So I'm curious about, instead of using Horovod, if you use PyTorch or TensorFlow's native distributed implementation, do you have any benchmarks on why one would use a Horovod instead of this? Apart from the ease of use.
Yeah.
Is there any difference in performance? Or
Personally, I didn't do the benchmark. So yeah, I don't know the performance part, but from the usability part, Horovod is much easier to use.
Because Horovod, the website initially claimed they were better than TensorFlow in scaling for high workloads.
So I did something using, so for example, TensorFlow, they use a so-called parameter server to do that. I see that in my GPU trainings, the parameter server, due to the I/O part, doesn't scale well. But however, you can see that we can let all the workers read the data simultaneously. So the I/O part is easy to do kind of in a parallel way. Yeah, that's what I found. But I have very limited experience of using a native distribution scheme in TensorFlow package. Mm-hmm. Any other question?
Are there standard tools to do the model parallelism as well, built into TensorFlow or PyTorch?
I think there's a package called Mesh TensorFlow, right? Mesh TensorFlow. It can do model parallelization. Yeah, but still I think it's in a development stage, not very mature. So as you can see, the model parallelization is typically very difficult to do. Like you need to make it in load balance way. Yeah, and then as the model become more and more complicated, it's just don't have a very good way to divide these neurons. Yeah, and then also another thing is that communication overhead is large, where you have a lot of data flow from one part of the neuron to the other part of the network. Yeah. Any other questions? Okay, thanks.